It's very important to master the 45-degree angle and to be able to work with vectors that are arranged to each other by multiples of 45, which is what's going on here. This problem is particularly simple, where vectors are arranged in such a way where the 45 degree almost doesn't matter. They're just perfectly arranged where there are clean sums and differences of each other and slight variations thereof. But the 45-degree angle is there, and by the time we get to the more difficult problems with a 45-degree angle, this practice will definitely help. So let's just go through each one of these one by one. So in the first one, we want the vector b as a linear combination of a and c. And what can I say? I think it's clear that b is exactly a plus c, whether you see it by the parallelogram rule or by the tip to tail. But I think this problem pretty much assumes that you can see that. So b equals a plus c, which means in terms of linear combinations that it's 1 of a plus 1 of c. Submit and enjoy the fireworks. Part B. We need to find c as a linear combination of b and d. C is right here, and b and d are right here. So what I see here, here's how I solve this problem. So c is definitely aligned with the sum of b plus d. In my mind, I can complete the parallelogram formed by b and d. It's actually a square. And I realize that what I will get when I add together b and d is twice c. So I need half of b and half of d, because I need not twice c, but precisely c, and b plus d is twice c. I need to take half of that sum, in other words, half of each of the vectors. And it's interesting here, I just want to make this note now, is that you don't need to think about the absolute lengths of these vectors. It's the relative lengths that matter. I think most of you imagine that vectors a, c, e, and g are length 1, and vectors b, d, f, and h are length square root of 2. And it's perfectly fine to imagine those numbers. The overall scale can be consistently changed by any number. So for instance, a, c, e, and g could be length 2, and the remaining vectors are length 2 times square root of 2. Or a, c, e, and g could be length square root of 2, and the rest of the vectors are length 2. It's not the absolute lengths that matter, but the relative lengths. That will be important for problems that we'll discuss later. Okay, let's submit this. Enjoy the fireworks. Moving on to C. E as a linear combination of A and C. E is a linear combination of A and C. Now this is a typical example of a problem that's made harder by being simpler. And the key here, of course, is that E, you only need A to produce E. You don't need any C. And if you don't need a vector in a linear combination, you give it a coefficient of 0. And the length, and because E is minus A gets the coefficient of -1. And so, here we go. Okay, D. Great. What do we have in D? F as a linear combination of B and D. Well, that's the same thing as C. F does not need both B and D in order to be decomposed. B alone is enough. And we need -1 of B plus 0D. Or, to say it in normal English, F is negative B, or minus B. I hope by now you're beginning to see that these are pretty simple. So let's talk about E. Hide the solution. I promise I did not look. Okay, let's see. E. We need to get H as a linear combination of C and H. Now talk about simple. This could be so simple that it's even harder to see. right? The simpler these problems get, the more difficult it may be to answer them. Well, h is just one of itself, even though nobody would say that in English. You would just say h is h. But if you have to say is h in the form of a linear combination, you have to say 1 of h and 0 of c. All right. F as a linear combination of a and c. Well, I think this is one of the more enjoyable ones. And it might be just slightly intimidating because f points in a completely opposite direction. At this point in your linear algebra careers, you may not be used to this kind of arrangement. But then you realize that f is just minus b. And we know exactly how to get b. b is a plus c. That was part A of this problem. It was a plus c. And because f is minus b, it has to be minus a minus c. Or, in the language of linear combinations, minus 1a minus 1c. Okay, moving on. G. Look at that. G as a linear combination of B and E. Ha! Could this be the hardest one of the bunch? G as a linear combination of B and E. Well, here's what I notice. If I do B plus E, I get C, which is minus G. B plus E is C, which is minus G. So in order to get G, I need to take minus B minus E. H as a linear combination of B and E. Well, here's what I see. I think this is probably the most interesting one because everything's looking every which way at some angle. But I noticed that E is very easy to express in terms of B and H. Now, that's not what the problem is asking for. The problem is asking for H in terms of B and E, which in my mind is hard. But if I get E as a linear is in terms of B and H, then I would be able to solve for H algebraically. So I think it's in these problems that you're beginning to see a very nice thing about linear algebra, how geometry meets algebra. And even though we're solving a geometric problem that ordinarily you would solve by making lots of drawings, we can actually solve by making a simple insight and then using algebra to get to the answer. So let me just use this field to do my algebra. So I know from before that E equals minus half B minus half H. And now all I need to do is solve for H algebraically. Multiply both sides by 2 and now solve for H. Minus 2 minus B minus 2E. So minus 2E minus B. Very nice. On to the next one. Try the solution. I. What do we have in I? D as a linear combination of F and G. D as a linear combination of F and G. Okay, here's what I notice. I notice that F is in the direction of the vector G from D. You see, we got to travel from D using the tip to tail way of thinking to F. And G is taking us in the right direction, but only halfway there. D plus G would land us right here at E. So we have to take D plus 2G. So F equals D plus 2G. Sorry that I'm doing in the middle of the whole thing, but I think that's okay. So now I have to solve for D. It's F minus 2G. So F gets a coefficient of 1 and G gets a coefficient of minus 2. Submit, enjoy the fireworks. Moving on. J. In J, we have to express A as a linear combination of F and D. Well, we've already done a problem exactly like this. It's a similar configuration, but just in a slightly different orientation. Submit. There you go. We've done this one before in a slightly different arrangement. K. In K, we have to express B as a linear combination of E and D. So it's similar to, I believe it was I, where we used one vector to travel from the tip of one of them to the other. But here I can see how get from D to B using E. I have to go to D and then subtract E and subtract E again. So it's D minus 2E, or minus 2E plus D. And finally, L. In L, we have to express D, where is it? D, as a linear combination of C and F. I think you can kind of tell how in writing these problems, I was almost running out of ideas. And so these arrangements are beginning to repeat themselves. But in any case, D as a linear combination of C and F. And I see exactly how to get D from C and F. You have to go to F and then add C once, add C twice. So we need 2 of C and 1 of F. Go. Done.